Oke, sekarang kita lanjut belajar embedded lagi.
The 123 microcontroller. There's the microcontroller right there, and in this video, let me show you the TM4C123 microcontroller. There's the microcontroller right there, and it has 43 pins. And what a pin is a way 43 microcontroller. There's the microcontroller right there, and it has 43 pins. And what a pin is a way, a connection for us to do input-output. And we see that there are 43 pins that we can use for input-output. Now what we have is a port. A port is a collection of pins that are grouped by function. So you see these 8 pins here are called port A, these 8 pins are called port B, we have
Collection, jadi port itu collection of pin with the same function. With the same function. Oke, jadi pin yang fungsinya sama itu digrup jadi satu, namanya satu port.
some in port C, we have some in port D, port E, and port F. Okay, so
Port E, port A, B, C, D, E, F. The channel 12 inputs.
a microcontroller is a single chip computer that has multiple pins for doing I/O. Now our launchpad is a board which has the TM4C3123 on it. Now it has an LED and a couple of switches that we're not going to use, but we bring this up for two reasons. First of all, there are 2 resistors on the launchpad labeled R9 and R10, and you're going to have to remove them in order to use the graphic display. And the second, remove them on the launchpad. Now it has an LED and a couple of switches that we're not going to use, but we bring this up for 2 reasons. First of all, there are 2 resistors on the launchpad labeled R9 and R10, and you're going to have to remove them in order to use the graphic display. And the second reason I show you this picture is to show you that the connection between the microcontroller and your PC occurs through the USB cable and through these 2 pins which implement serial communication.
So John, can you tell us a little bit about
Sedikit review. Kemarin port itu ada 4 jenis: serial, digital atau paralel. Terus ada time, sama yang terakhir itu ada analog. Ada 4 ya.
how serial works?
The basic idea of serial is we encode the information in the voltage dimension as a true and a false. And in the time dimension, this signal will oscillate or change as we are transmitted information. So if we were to look on one of these pins, we would see the information encoded as a digital value which varies in time. All right, now let's look at the specific implementation that has our launchpad together with the booster pack for the labs. And we'll learn more about the booster pack later, but let's make a list of the types of I/O that you will see in this class. The first is digital I/O,
Digital itu paralel.
which we're going to call general purpose input-output, and these pins here are input pins. We have some digital pins, which are output. We saw last time that there was some serial pins, and so this is a serial port which we can transmit and receive, and that's serial. Again, that's digital serial. There is a equivalent or similar device which is serial, which we'll use to connect to the Bluetooth device. There are 2 other types of serial devices we'll see in this class. One is used for collecting information from sensors, and that is called I2C. We'll see another serial device which is connected up to our display, which is synchronous serial. So there are 4 types of serial devices on our device.
SSI common. Synchronous serial interface. Di serial communication tuh ada beberapa yang udah kita tahu, ada I2C, UART, sama ini ada baru namanya SSI, Synchronous Serial Interface.
And lastly, we have a large collection of analog devices. Analog signals are such that they vary. The information is a voltage, and it varies in time in a continuous fashion. And that is used, again, for additional sensors for our system. We have one more. It's an output device, and it's called pulse width modulation.
PWM.
And pulse width modulation is connected up to our buzzer, and basically what we have here is the ability to change both the frequency, which will affect the pitch, and the duty cycle, which will affect the amplitude of the sound. So in summary, what we have is a microcontroller which has multiple pins. The TM4C123 has 43 pins, and those pins have certain functions: digital input, digital output, 3 different types of serial devices, an analog device, and a pulse width modulated output. And altogether, this performs our system.
And as we will show you the board support package, make sure that you don't have to know all the low-level details. We abstract these devices for you, and we'll show you how you can manipulate these devices.
Oke, mari kita cek dulu. Ya, ada port 8 UART, 8 UARTs, 8 tambah 4 12, 18, 18 tambah 16 34, 18 tambah 16 34, 34 tambah 5 39. Tapi kok katanya ada 43. Online 8 12 plus 6 24 32. Ini kayaknya salah ya, harusnya ini 12. 8 UARTs for SSI. UART to PC. Mana UART to PC ini? Light sensor input. Tadi ada yang suruh ngilangin resistor. Wow. Ini ada bukunya ternyata. Wait, kita lupa buat set timer. Timer for 30 minutes. Okay. Device or host. Oke, lanjut.
In this video, I'm going to show you how to remove R9 and R10. These two resistors jumper a pin between port D and port B, and if we want to use both of those pins, we got to get those resistors off. So I got a soldering iron, and I'm going to heat up both sides. So it's going to get hotter. All right, let's go hotter. works. Oh, it's off.
Do it.
It's off. It's gone. Okay, so the audio wasn't real good, but all right, let's try again. All right, there goes R10. So to get the resistors off, I'm going to use a soldering iron. One's enough, and the key will be to heat up both sides. So I'm going to heat up one side until I see the solder flow, and I'll heat up the other side until I see the solder flow. They're pretty small resistors, so they will come off. And there we go. R9 is off. So to repeat, to get it off, I use a soldering iron. I heat one side till it's hot, and I see the solder flowing, and then I heat the other side, and then since it's so small, they should come right off.
Two switches. One trigger already. Yes, ma'am. 114 and 1. Okay. Terserah teman. Di stack gitu ya. adafruit.com. Item number. Because we don't need to use the switch and also the LEDs, and you want to use that individual pin. PB9 to PB. Yeah, to use our. Yeah.
So with this video, let me show you some of the features of the MSP432 and how we're going to use them in this class. Now there are 84 pins on this processor, which means it has a lot of capabilities. We're going to show you just some of those features here in this video. So here's the launch pad. There's the MSP432 microcontroller, and this is the debugger, the JTAG debugger we're going to use. Now, the I/O that we're going to focus on in this class is centered around these 40 pins, which will connect up to the booster pack. Now, there are 2 buttons, 2 switches, and 2 LEDs on this board, but we won't be using them in this class. So this shows you the block diagram of the MSP432 Launchpad. And as I said, we won't use the 2 switches or the 2 LEDs for doing the labs. We'll use the onboard lights and switches of the booster pack. But we are going to use the serial port here on the MS432 in order to connect up to the PC. And it's on that channel that we're going to implement the grader and the logic analyzer. So here's an outline of all the devices that we're going to use in the labs this semester. And as you can see, there's a lot of different types of I.O. The simple I.O. is general purpose input-output, which we can use for our buttons as inputs or our LEDs as outputs. There's a number of more sophisticated I.O. like I2C, which we're going to use to implement the light sensor and the temperature sensor. And you notice that both the light and temperature use the same port, so our operating system is going to have to manage that connection. There are other devices like the synchronous serial port, which we'll use to connect up the liquid crystal display, the PWM, which will generate sounds, the UART here that I already talked about, but there's a second UART we'll use in Lab 6 to connect up to the Bluetooth module. And then there's a whole sequence of analog pins, and these are connected up to sensors. For example, the microphone to measure sound, the joystick to measure XY position, and the accelerometer that we'll use to measure steps. And here in this class, we're going to write our operating system to manage these I.O. devices. And one of the interesting features is speed. It turns out some of these sensors are really, really slow. Okay? The light sensor and the temperature sensor are very slow. They operate on once a second. And then the accelerometer is a medium speed device, which operates on 10 to 20 times per second. And then the microphone is a very fast device, which operates in thousands of samples per second. And again, our operating system is going to be needed to manage this complexity.
Okay, let me see this. Yeah, you are to Bluetooth. Yeah, temperature I square C, LCD, SPI. I'm not sure if this is SPI or SSI. Button to input. Enggak, intinya kita nggak pakai ini. Oh, right. This is just another. Oh, ini port lainnya. Oke, kita nggak pakai ini, jadi kita bisa next. We sure about it? Yes. Oh, kita assembly again. Ya, X, EDX, AD. Register. Okay.
So we're going to look at assembly language.
Do we have to?
Yes, there's a lot of stuff in this class that can be done at a high-level language like C, but there are a few things, very few, maybe a couple of, maybe 20, 30 lines, 40 lines of code that have to be written at the lowest.
Assembly buat x86, sekarang belajar buat yang assembly untuk ARM. Assembly, catat dulu. On ARM processor.
Level, which is in assembly. And so let's look at assembly on the ARM. So it turns out the ARM instruction set has 200 plus instructions. There's no way we're going to get through all of those instructions.
Ada 200 lebih instruction.
So we want to give you a sense of what it means to write code in assembly. So assembly instruction, an instruction in ARM assembly looks something like this. There's a label. There is an operation, we call it the opcode.
Label, opcode.
it has a set of operands, one or more operands, and any comments you want to put. So this is what a line in assembly looks like. Now, turns out the comment and label are optional. Optional as in there are some lines that have labels, some lines that do not. Most lines should have comments if you're a good programmer, but the language doesn't require that there be comments. Operands similarly are have to be, there's 0 or more operands. There are very few instructions, maybe a handful, that have no operands. Most operations will have at least one operand. So let's take a classic instruction that we will be using because our processor is what we call as a load store architecture, which means a lot of things that we will do will have involved loading from the processor and the memory. We will load things into memory, into processor, and we will store. So this is our load, and that's our store. So a significant part of doing processing on our machine involves loading something, processing it in the processor, and storing back. The processing itself may entail some arithmetic operations or logic operations or so on. So the way we're going to look at load store is by showing you something that you already are familiar with, which is in C. If I write a statement like this, let's say I have a statement that says count equals count plus 1. This is an operation I want to perform. Let's see how we perform this operation in assembly.
And we're going to assume here that count is a 32-bit variable located in global memory.
So count is somewhere in RAM, and it's taking up
in assembly
4 bytes. And
kenapa 4 byte? Karena ARM Cortex ini 32 bit prosesor, 32 bit itu 4 bytes. Jadi word size-nya 32 bit alias 4 bytes. Counts.
We want to see whatever count originally was, we want to take count, load it, manipulate it, and store it back. So we do that by these set of instructions. So I do a LDR instruction, and I first try to get
load RAM.
I get the contents or the address of count into a register. So what this instruction, look at the syntax, it says LDR is our instruction. It has 2 operands. One is the destination register, and the other it says LDR is our instruction. It has 2 operands into a register. Get I instructions. So I do a LDR instruction, and I first try to get the contents or the address of count into a register. So what this instruction, look at the syntax, it says LDR is our instruction. It has 2 operands. One is the destination register, and the other is the equals tells you to look at count, fetch the address of count, and put it into the destination register. So this instruction will get, so if count happens to be at address 0x2000 0100, at this point R0 has the value 0x2000 0100.
So it doesn't have the value of the variable, but the address or a pointer to it.
That's correct. So the next thing we're going to do is we're going to fetch the contents of it because we want to modify what is count. So to do that, we use another register, and we say fetch the contents of that address. So this syntax says the second operand is treat the register as an address and go to that memory location and fetch the contents of that location and put it in R1. So assuming count had the number 42, what R1 will get at this point is
42.
Value 42.
Okay.
One of the consequences of a load store architecture is we will do operations, manipulations, not in memory, but do them on registers. So how do we add one, Professor Yarvali?
So we have an arithmetic operation, the processing we want to do. We say add R1. In this case, we want to add 1 to it, and the syntax says add. Here's a source register and the destination register. So what this one does is it takes R1 and adds 1 to it and puts the result back in R1.
So you'll find all the operations, all the mathematical calculations are not done on memory, but done on registers.
Yes. And then now we're going to store this result back into memory. Remember that we already have the address in R0. We say store the contents of R1 into memory at location that R0 holds.
LDR is load, STR is store. Store TR.
Which will, we say store the contents of R1 into memory at location that R0 holds, which will result in the value of count now becoming 43 because R2 was 40, R1 was 43, and that's what is being written to memory. Now, just a quick note on these. There is a version of LDR with our R1, R0. Here, R0 is assuming what we call as, this is called the base, and it has an offset, and the offset is assumed to be 0 if you don't mention it. So in essence, what this instruction did is it went to memory, fetched the contents of the address in R0 with added 0, and put this into R1. Now you can specify an offset, and you can do that by saying LDR R1 with an R0 and a offset. For example, if I want to get to a location that is 4 bytes away from it, I'd use that, and this is the offset. So this then will go to memory with the contents of R0 as the address, add 4 to it, and fetch the contents of that and put it in R1. So now that we know how to do load store operations, let's take a look at what another common thing we do in C. In C, a function call is a fundamental operation. So what I do in C, for example, is I call a function of some kind, and I'm going to keep it as simple as possible. This is a function that takes no input. It's a void function, which means it takes no inputs and it returns no outputs. So how does this work in assembly? In assembly, a function is nothing but a label, and it has a return at the end. An instruction for the return is called BXLR. This is saying branch to the link register. And we talked about the link register holding the return address. So to call this, in my assembly, I will say BL function. So the BL here says branch, but keep a link to where you came from. So the link register will hold the address of the next instruction. So what's going to happen then is control goes there, we execute the instruction, and when it does a BXLR, because LR is holding the return address.
BXLR is BXLR is returned.
Control comes there, and we continue executing. The one feature in assembly that we don't have a direct correspondence to C is the use of the stack. And the stack for us is a region of memory which we saw before, where the stack pointer is pointing to the bottom of the stack region, and we do operations which are push and pop operations. And we've introduced these operations to you. The syntax or the syntax of these assembly instructions is we can put our set of registers that we want to push in curly braces, and we specify, for example, R4 through R11. The minus here is saying that it's a range, not subtract these two, but it's a range. So take not just R4, but R4, R5, R6, R7, R8, all the way up to R11. Push all of these registers on the stack. So the contents of all of them will be pushed on the stack, and the stack pointer will point to the top of it. So the contents of R11 will sit here all the way to R4, R5 here.
So when the rule is when you push multiple registers, the register with the smaller number goes at the lower address.
And that also applies to pop. So if I'm doing a pop, it's the same thing. I can say R4 through R11 again if I want to pop, and it's going to pop the lower memory location. So low as in, remember, this is high as we go down, and this is low. So the lower address value goes into R4, and the higher address value goes into the last one, which is R11. So it's also possible, this is a more generic version, but it's also possible for us to do push and pop on individual registers. For example, there might be a scenario where
How do the stack go? High address to low address, yeah. Dari atas ke bawah.
I'll just want to put the link register on the stack. And this is usually done when if I'm going to call a subroutine of some kind, function, and if this itself is some other function within some other function, I am writing a call to a function called function, then I don't want to lose my return address. So what I do is I push it, I call it, I pop it back when I return so that my BXLR at the end will have a proper home to return to.
And again, it doesn't matter what order you list the registers in this list. You can have 1, 2, or all of them. But what matters is when they're on the stack, they get put into the order according to the register number. And so they're popped off, in this case with R4 on the top, because R4 is less than R14.
So these are pretty much the instructions you would need to know. Any other instructions you need, you can pick up as you go along. There are, for example, instructions like the CPSID, I, and CPSIEI, which basically clear or set the I bit, which enables or disables our interrupts. So you'll learn these instructions as the need arises.
Okay, nice. Label. Add R0, R1. Yeah, okay. EQU. LDR load STR, LDR load register, STR store from register, move register, push pop, B back, I think. BL is push to link register, BX pop from register, add subtract. Okay, I don't know what's B. Let's search for them. B instruction in ARM. B instruction is the same as jump. Oh, jump. So it's like percabangan, branch. Okay. B is for branch. Oh, BL is branch link, branch back. Okay, nice. Addressing modes is it bot link? Why this is not marked as complete?
So we're gonna look at our disables our interrupts.
Okay. Addressing modes. No, addressing modes is whether this data or depend. See if I have addressing immediate data within the instruction. Move R0 into R0 value of 1 index. Data pointed to by register. Okay. Kayak access array, index with offset, access array with offset. PC relative, program counter relative, location is offset relative to program. BL increment. Oke. Jadi BL berarti BL itu branch link address, link register with increment. This incrementnya ini bakal apa namanya, offset dari program counternya. Kayak buat loop ya, kayaknya ini buat loop. Kayaknya register list of register push. Wait, what? Oh, R4 to RLR. No addressing mode. No memory data fetch. Add R1, R2, R3. Oh, add destination R1, operannya R2, R3. Immediate nggak perlu. Oh, langsung move R0 1. Index ya, index tuh kayak array. Ya, ini untuk branching kan, branching namanya for atau if ya. What does addressing mode specify? Addressing mode specify how does the data access into the registers or memory. Yep, pretty much it. Next, we will only need 12 our real time. Okay, we will need the following for load and store instructions. Load register RD with the value pointed by Rn. Store with the offset, this one also offset. Let M be the 32-bit value specified by 12-bit constant. Immediate M 12-bit constant. Why 12-bit? Move data to RD from Rn. Move data to RD. Oh, why 12-bit? But because register size in ARM Cortex M4. Why it's only? Aku kira tadi itu Why it's 12 bit? Because I thought that the register size would be 12 bit, but at MSP 40 digit key. Lupa tipenya, namanya MSP. TMC this, or I just check, just click. Klik di sini. ARM Cortex M4F. Oh, 32 bit register. Immediate value in ARM Cortex M4F. Okay, I don't know why. Add ke RD, RN dan RM. RN tambah RM sama dengan RD. Oh sorry, RD sama dengan ini. RD sama dengan RN tambah immediate. Oke, RD sama dengan RN tambah RM. Oh, subtract RN dari RM. RD RN minus RM. RD RM minus M. Oke. CPS ID disable, ya, IE enable to 0. Oke. B itu branch, ya kan? BX itu branch back to RM. Oh, branch to label, and this one is to RM. RM if BX LR link register berarti itu return. BL label itu ini subroutine. Add label, ya ini branch juga. What is the difference between B and BL instruction in ARM Cortex? Branch with link copies the address of the next instruction to the link register. Oh, okay, branch with link. Link register itu buat nyimpen return address. Jadi kalau ini branch doang, tapi kalau ini branch with return berarti biasanya digunakan untuk function. Maksudnya function call. Push pop oke lah ya, push RN isinya RM. RN oh ini N pop RN 232 bit. Oke. Push R1 dan oh timer is up. Oke. Kita sholat dulu ya guys. Akmal sholat maghrib dulu. let's continue our study. Oke, udah ya. 1. Wait, what? Harusnya menurutku ini salah. I don't know. Harusnya 1 masuknya di bawah nggak sih? 1, 4, 5, 6. Terus jadinya Bentar, baca dulu. Oke, consider value of push. Pokoknya register yang paling kecil itu di paling atas stack alias di address yang paling kecil. Figure so the value from the lowest stack address is loaded into the lowest number. Oke, berarti lowest address, ini jadinya popnya ini dulu, terus ini ini dulu, terus pop ini baru pop masukin situ. Oke. Cancel. Next. Accessing memory. Mana videonya? Video di bawah. Mana bahasa introducing and writing global variables since consider a simple operation of incrementing a global variable input C and ya intinya gitu kan. Intinya di load dulu, load R0 address dari count. Sekarang R0 punya count, sekarang load R1 dengan isinya si R0 alias si countnya itu sendiri. Terus add 1, di situ store isi dari R1 ke isi dari R0. Store R1 load register. Oke. Assume run pt points to a linked list. Okay, linked list. A node of the list is a structure with multiple entries of different types. Okay, and the linked list is a set of nodes. Okay, next entry. Run pt itu linked list. Okay. Ya, program counter relative. Sekarang ini oke. Terus intinya si run pt di load ke R0, terus load R2, si R0 ditambah 4. Kenapa loadnya enggak R1? Kenapa R0? Store R2 isinya R1. Oke, ini ilustrasinya. Initially like this. Addressnya. Sekarang R0 itu point ke jadi isinya R1. Isinya R1 adalah si run pt itu sendiri. What is yellow? First, second LDR R0 load ke R0, isinya R1 which is run pt itu sendiri. Ya oke, run pt merah makanya set load R2 R0 tambah 4 geser 1 kan. Finally store R2 wait initially finally. Oh ini linked list, wait this kayaknya harus baca dulu. R0 tambah 4 itu sini. Terus store R2 ke isinya R1. Isinya R1 adalah si run pt. Awalnya dia point ke sini, sekarang dia point ke sini. Ya ada video sekarang.
Hi, while we're talking about assembly language, let me introduce a problem.
Ya kalau aku udah paham.
These words are also used in RAM, and we want these words in RAM or creates
Paham.
make a pointer to that variable into the register. And so this variable, but the next step makes it worse. And we're going to have to solve this problem. We'll see it in detail in the next chapter, and it's called a critical section, and we'll figure out how to solve it, and we'll talk about it in more detail. But while we're talking about assembly language, I just like to point out that this particular instruction right there is the one that caused the situation. Because we loaded data out of memory and put it in a register, and we didn't actually move the data. All we did is made a copy of it. That created 2 copies of the variable. And our operating system is going to have to solve this problem.
Ya oke, paham. Next function. Alhamdulillah. Import model address because they allow us to develop modular program language Pascal with an additional function with return value. Oh wait, aku lupa buat timer lagi. Let's make it 45 minutes. On the other hand, between function which return values and procedure which do not. Okay. On the other hand, C do not make and treat as synonymous. The method object being instantiation of class in assembly language, we use the term subroutine for all subprogram, whether or not they return. Okay, modular programming. Following by introduction, BXLR. BX is back to okay. Return. Space. The function in program 1.1. 1.1. Oh. The area data directory specified. Space for sudo. area code. Oh, ini area data, ini area. For uninitialized bytes, 4 bytes. Okay. The area code directive ROM. Let's connect this program to the C. Line 2 will force the machine code to be half word aligned as required. Satu wordnya 32 bit, half wordnya berarti 16 bit. Is that correct? I don't know. Let's see. In use PL. Ya, PL itu branch and store the return address to link register. Save, ya, betul. The return address is the location of the instruction immediately after BL. Oke, setelah BL instruction itu apa? At the end of the subroutine. Ya, oke, paham. Countnya di route addressnya dulu, habis itu countnya masuk, R1 ditambah, terus store is R1 ke isinya R0. Oke, terus BXLR balik ke link registernya. Oh, ini fungsinya BXLR return, intinya gitu. Oke, start, ini start dulu, habis start load register R0 count, move R1 immediate 0, and then start R1. Okay, and then BL function. BL berarti branch with link register to function, which is this one. Set BXLR, baliknya setelahnya BL berarti B loop, balik ke loop, eksekusi lagi gitu terus. Oke, ya paham. It doesn't pause if one function were to call second function because there's no system. Oke, berarti dia push dulu kan, push R4 link register, R4 register PL function BXLR pop. Oke, ya paham. When software calls a function, where is the return address of link register or LR? Yeah. Next, the ARM architecture. Bentar guys, mau cek dulu, masih kurang berapa ya kita. Pointer debugging, ternyata banyak ya yang perlu dipelajari.
So John, in this class we're using both C and assembly. Do you have to pay any attention to this mix of two languages?
Yes, because the C is generated by the compiler and the assembly is written by you, we must follow a structure in order to be able to...
So John, in this class we're using... Do you have to...
Yes, because the...
Alright guys. Wait. Okay, it's not responding. I just close this and then
we were going to classify...
So John, in this class we're using both C and assembly. Do you have to pay any attention to this mix of two languages?
Yes, because the C is generated by the compiler and the assembly is written by you, we must follow a structure in order to be able to connect programs written in C with those in assembly. And luckily for us, ARM has created what they call the ARM Architecture Procedure Call Standard. And this is a set of rules, some of which we're going to show to you today, that you must follow in order to properly connect C with assembly. So let's look at those rules. The first, interestingly enough, is when we have input parameters. Okay? If a function has input parameters, the first parameter is in R0. The second one, if it exists, will be in R1. The third one in R2. And the fourth, if it exists, will be in R3. And we won't worry about if there's more than 4 parameters. That's the first rule. The second rule, as you know, in C, functions can have an output parameter, can have an output return type in R0. C with assembly. So let's look at those rules. The first, interestingly enough, is when we have input parameters. Okay? If a function has input parameters, the first parameter is in R0. The second one, if it exists, will be in R1. The third one in R2. And the fourth, if it exists, will be in R3. And we won't worry about if there's more than 4 parameters. That's the first rule, 3. And we won't worry about if there's more than 4 parameters. That's the first rule. The second rule, as you know, in C, functions can have an output parameter, can have an output return type. And in order to follow the structure, we will use R0 if there is a return parameter as the output parameter. That's the second rule. The third rule is an interesting rule that has to do with register uses. We were going to classify R0 through R3 as free variables, free registers. That means that any function can use and destroy these registers as they want. But a function, if it were to use R4 through R11, must preserve these registers. And as we saw last time, a function can preserve these registers by pushing them on the stack and then popping them off at the end. Oh, and R12. R12 is a free variable. Forgot one. Okay? The next rule has to do with stack. Now, in order to make it run faster, and that's the reason why we do it, the stack is going to be aligned to 64 bits. What that means for us is whenever we push something on the stack, we will push an even number of registers, 64 bits. Is going to run faster, and that's the reason why we do it. The stack is going to be aligned to 64 bits. What that means for us is whenever we push something on the stack, we will push an even number of registers. So this is a valid rule according to the ARM Architecture Procedure Call Standard. Whereas if we do something and we push just one register, this is a violation of the rule. So we will see in this class, whenever we need to push and pop registers, we will use an even number of registers.
Why?
So to summarize, what AAPCS is really giving us is the linkage between C and assembly. Remember that the only time we have to worry about this is when control is transferred from C to assembly or assembly to C. And the only way we can transfer control is by calling a function, whether we call a C calls assembly function or the assembly calls C function. So that's the reason why we're only focusing on the call and what are the rules that one has to follow when making these calls.
Recall that all object code is half word aligned. Wait, what is the word size in RMM for F? Yeah, I know. Word size in RMM for F. 32 bit, berarti half wordnya 16 bit alias 2 byte. All object code is half word. Business Organizer LR. Yeah, dan ik is dat leuk dat bit 0 is set to 1. Oke, 8 byte. Oke, paham. Because it's half word aligned, it means the bit 0 is always 0. Oke, paham. Oke, kita draw IO ya. Learning diagram, documents. Let's create new folder, learning, and inside the folder let's processor. Let's just put here embedded learning. Oke, jadi sini kan address 0. Okay, let's make it 0x 000. (32 bits). 32 bit, it means 8 byte. So no. That's 2 bit. Sorry, 2 byte. Right? Hexadesimal 16 itu 4 bit. 4 328 berarti kan 4 3 4 6 4. Because it is half word aligned, half word. What's the meaning of half word? Half word itu 8 bit. 8 bit means number. No, not 8 bit, 16 bit. 16 bit ditambah 16. 16. 1 2 3 4 5 6 7 8 bytes. Okay, because of its half word, so half word itu 16 tambah 16. 16 itu berarti 1 2. Kayaknya let's make it 0b. No, just like this. 16 it means like this, right? Because it's half word aligned. Jadi ini address, ini program counter pertama. Program counter saat pertama, kedua, DST titik. Nah, karena ini half word align, selisihnya selalu half word, which means the difference is always the multiple of 16 decimal. How to make it decimal? 16 decimal, which is 0x10. It means the LSB is always 0. Benar, agak saja benar. That's my understanding. What is the purpose of AAPTS? AAPTS itu untuk to align the code compiled from C with the assembly code we generate. Okay, next. Oh my god, there are so many videos.
So John, what are we going to learn today?
Today, we're going to learn about the board support package. And this is our way to abstract the devices on the booster pack so that we can focus on the operating system and not worry about the low-level details. We saw in previous videos that the microcontroller had pins, and the pins had different types. What we're going to do in this video is to show you how your code is going to perform input-output for the devices on the booster pack.
So this picture is showing us this process with an example of a launch pad.
Yep. And the particular launch pad we're going to see is the TM4C123. But everything we say today will work either on the 432, the MSB 432, or the TM4C123. All right, so let's begin with the buttons. Okay. Now, on your booster pack, there are two buttons, button 1 and button 2. And in order to use the button, we will first call the initialization function to turn it on. And then when we want to know the value of that button, we will call this function, and it will return a Boolean, true, if the button is not pack. There are two buttons, button 1 and button 2. And in order to use the button, we will first call the initialization function to turn it on. And then when we want to know the value of that button, we will call this function, and it will return a Boolean, true, if the button is not pressed, and a 0 if the button is pressed. That's negative logic. And there's similar functions for button 2. So again, there are the buttons. The next device I'd like to talk about buttons. The next device I'd like to talk about is the joystick. That's this big black thing here, which can vary back and forth. Okay, so you can move it back and forth, and you can push it straight down. The beeping actually is another function. You can move it back and forth, and you can push it straight down. The beeping actually is another function, but pressing it straight down is essentially a third switch that you can use in your program. So just like all the other devices, in order to use a device in the interface, you have to call the initialization function. And you call that once at the beginning. And then anytime during the running of your system, if you want to know the value of the joystick, you will call this function and pass in 3 pointers. This is called by reference. Pass in 3 pointers, and it will return to you in those values the X position, which goes from 0 to 1023, the Y position, 0 to 1023, and then the status of the button. Again, 0 means pressed. And if you look at the screen right here, you can see that this example program is plotting out the values of the joystick. So if I move it to the right, the number changes. I move it to the left, the X changes. I move it up, and I move it down. We can see that these two parameters are available for the software. The LED is over here. You can see it's currently outputting a red, and it is a 3-color LED. And we will call the initialization function to initialize it. And then anytime you want to change the LED value, your code will call this function here and pass in 3 different
different on a blue color.
There's 8 different colors that you can generate by combining these 3 booleans.
Oh, digital.
All right. We already heard the buzzer. There's the buzzer over here. And the buzzer software is pretty simple. It's set up to initially generate a 2.048 kilohertz sound. And after you initialize it, what you can do is change the loudness, and such that 0 will make it quiet, and 512 will make it the loudest. So you can hear the buzzer. The software is calling this buzzer twice, once to make it start with a 512, and once to make it stop buzzing with a 0.
So a 50% duty cycle will look like it's on for exactly as much time as it's off. And that's a 50% duty cycle, which, by the way, creates the loudest sound we can get.
Again, it's about 2 kilohertz. There are a number of sensors on this board, which is why we've chosen it for this class. And so let's run through the sensors. Embedded on this device is an accelerometer. Okay? And after we initialize it, if the software wants to know what the acceleration is, it'll pass the acceleration plotted out. We're going to use to measure, basically, right, turn 3 different dimensions. The microphone is another fascinating things about this application is we see that the sensors work on different times. The accelerometer is something we'll measure about 10 times a second, and the sound is something we'll measure at least 1,000 times per second. The software is called by reference, and it will tell you a number which represents the current loudness of that sound. And so the data here will look like that in terms of amplitude versus time. And that will be our sound measurement. In this case, we're just looking at numbers and letters, but in subsequent labs, we'll have plots or data plotted as a function of time on it. The LCD is fairly complicated. There are lots and lots of functions. The initialization function obviously initializes it. The fill screen allows you to fill the entire screen with a single color. It is a 16-bit color system, so all of the pixels on the device are 16 bits.
16-bit color system. So RGBA.
And this function here will convert the standard 24-bit color, red, green, blue, into the corresponding 16-bit color that this function uses. The dimensions of the screen, in this dimension it goes from 0 to 1,000 to 127, and in this dimension it goes from 0 to 127. So there's 128 by 128 16-bit pixels on the LCD. Lots and lots of functions. If we want to draw a string on the screen, we can choose a spot where to put it, and we can choose a string to plot and a color to plot it with. When we're outputting numbers and characters, we can set the cursor to the column location, 1 through about 17, or the row location, again from about, I guess actually 0 to 17, from about 0 to 17 again in that dimension. We will be outputting numbers, and we can out them as decimals, or we can output them as fixed point numbers. When we get to lab 1, there's a complicated way for drawing pictures. We will set up the axes in terms of the color you want for the axis, various labels you want to put on the plot, various colors of those labels, and various dimensions that we're going to try to plot. And while it's running, we will be able to plot certain points, either 1 point or 2 points onto each of that plot, and be able to control the x dimension. We're going to talk more about these functions when we describe how to do lab 1.
The word board functions can be kind of, as I said, categorized as at a pixel level.
And the fun, the same. And it measures the amount of ambient light. Say, Justin, is it bright in here, isn't it? Was to abstract or to remove the light. Use the I2C interface. And I mentioned before that there was a discrepancy in the speed of these devices. We saw that the microphone was on the order of kilohertz, the accelerometer on the order of 10 hertz. Now, these two sensors are very slow. They operate less than a hertz. And so we're going to have 4 sensors with very different speeds. And in order to collect data, we're going to initialize it. We're going to, since it is so slow, what we're going to see is we're going to set one function to begin a process, and about a second later, we can look and see if it's done and get the value of that information. So again, this is a very slow set of sensors that measure the light and the temperature. Lastly, I'd like to just show you some available functions. These are the ones we're going to see in Lab 1. Again, the point of the board support package was to abstract or to remove the low-level details. So what we're going to see here is the user code, which is going to be sit on top of UI, and we're going to design this in such a way that the exact same RTOS and the exact same fitness device will run either on the TM4C123 or on the MSP4. It's the only difference, and that's say microcontroller on the TM4 device actually 432. Lab 1 is abstract package, and in this class we're going to focus up on at this level of the design, into the RTOS, into the user, and the board support package is going to hide the details of the physical hardware from us. So in this video, let's look at the board support package from another level. Okay, we have 2 launch pads. One's the MSP432, one is the TM4C123, both connected up to this MK2 booster pack, and they are running the exact same main program that is illustrated here. So this is the same main program which is running on both of them. The exact same main program that is illustrated here. So this, if you want to see, look in here. This is a call values from the accelerometer, the reading. Is making the board reading the input from the other switch. The main program here is the initialization. This is making the board run the fastest as it can, 80 megahertz on one and 48 megahertz on the other. There's the rest of the initializations. And down here are some outputs, character outputs, to the liquid crystal display. So in summary, what we've includes the board implementation, and that in the operate fitness to launchpad.
Okay. Okay. Button, the initialization to button. Okay, so what's the problem here? BSP joystick. Yeah, is it this spec, right? Not spec. Yeah, technical specification. LEDs, buzzer, yeah. Accelerometer, microphone. Alright, are we looking at LCD graphics? Right ya, mama lihat line dulu. Ada line yang sangat cukup berisik. Okay, let's go. BSP start done while done equals 0. Okay. Mutual exclusive access, which is mutex in assembly. Fast switches, LED microphone, joystick buzzer, light and temperature. Lapar guys. Processor clock. Okay. Pointers. Ya, udah tau lah ya. Let's see.
Professor Yerobawi, what are we going to learn in this video? So we're going to take a step back and get some of the fundamentals squared off. So we'll look at how declarations work, whether they're simple declarations or declarations that involve pointers, declarations that involve function pointers, and we'll focus a little bit on pointers because it's a concept that's going to recur a lot in this class. So when I see a C declaration of a variable, so let's take a declaration of a variable. So when I declare a variable in C, where I say int count, what I'm the system count inside RAM for it. Something else, a star, I am declaring ET to here thing in a different way, which is what is interesting because I can also read this as CPT, star CPT is a int. So which is interesting because what I did by declaring CPT as a star CPT is I'm saying there is a pointer somewhere in memory and it's going to point, it's going to hold an address which is an address to an int. So somewhere if I have a in the pointer to an int, it doesn't matter where an int, I could do something like the state equal count.
Yeah,
Well,
okay,
the pointer, which is say it was then C00 that add to initial trying to after this declaration what you that's what I mean now that I have the 2 location which is e but I have which is if I look at star CPT is this operator D is the act so is the point R in front of this value is I be the same time one is through the point as we go along make an appearance so how to get the fine take a look at one of the so we can by call is if I count and it incremented function looks something like variable which and only had the result of this from copied as a value of 15 so the thing is the value sense is the pointer now if I were to increment and I'm going to pass as the value address of this gets ends up happening value and become 4 whereof in the we will talk at length the other uses data structures and maybe even implementing your own structure of
okay, thank you, that's a great video. What are pointer is a variables that hold the value of an address hold an address as the value. And why they're important? They're important because it is used to manipulate the inside of the pointers. Can I say that? Regardless of the scope. So it's used to return a value from a function, something like that. Address, yep. Not more data with a single, yep.
So we talked about pointers and I said that the pointers are the foundation for doing arrays. So we know an array is simply defined as a collection of items. This collection is so if I am correct and first I'm going to say initialize list just leave it is going to memory prime the start minus 1 the values. If I simply refer to the word primes, if I said something like if I'm using let's say a assignment statement something like CPT equals primes, what I'm really doing is I am fetching the address of this. So primes is the address. In fact what it is primes is a synonym for the address of primes of 0 but to primes which is a star declared which means that I can the value getting to the second element which is supposed to plus to use so pointer and about where address plus this is necessary.
What is the range of index value used to access data 0 to 9? Linked lists. Okay, this is I don't like this.
Let me show you linked lists. Linked lists is another example of pointers. And linked lists are used in real-time operating systems because it's a way to store information. And with a linked list, we have a list. And what a list is a structure which has at least 2 components. It's going to have data. In our simple case, it's just going to be a 132-bit element. And it also has a pointer called next. Okay, so this is a list. Okay, it has 2 fields, and they are not necessarily number. And that list, it also has 3 pieces of data. I'm going to store a 1 here somehow, and 10 and 100. Okay? And now I need some special magic to tell the system that there's only 3 elements. And so I'm going to put in what's called a null pointer. And Professor Yarabali told you that last time. The address of 0 is going to mean not an address or null. I need one more important piece of information, and that is I need a way to find it. Okay? And so what we often have is called a head pointer on a linked list, and the head pointer. All right, so let's show you first let's create the node. And the structure is a way to having the first element in the first field. So we'll put in
the data, which is the payload, can be anything. Here we're just calling it the task.
Anything yet? All we've defined a new type. No, and I like to use type defs. All right, so now I have a new type. And so head pointer is a pointer to it. Have fun with this linked list. So let's make another fun with this link pointers.
We actually use an element link that is
Okay, there's the easy way.
easy way.
We're going to make the execute list static case an array linked list.
Location by
Here I read the first one. Another brace from it. And store it into the okay, and I'll give it its parenthesis. Okay, and I'll give it its value.
has another
There into the address. I just created just soon we could get there. Let's say I wanted to create or initialize my head pointer to point to the first element. Now we already created it, so at runtime I'm going to create the following assignment statement. Head pointer equals list.
number is just the address.
Generates the long. One of the fun things we can do with linked lists is go to the next element. Build the arrow, get the next, create, write it back into line of code. All right, let's do that. Search particular data in or inside because it's not. We'll need that's pointing to it's in there. Going to do is a 0. So if this pointer ever becomes 0, it'll quit. Up to the data field. Remember what I wanted to do. Now, if the pointer pointing to the data is equal to get it to point to the next, and if it quits all the way through, then I know it's not correct. If I pass in, look there, and look here.
Okay.
Pointer.
In the array element was the first initialize the array so that the first element pointer, third element could have pointer. Now change the ordering list, and that wouldn't be
An example box of a execution. That's how we're going to play with these.
What is a linked list and what ways is it better than an array? Coordinate statically. Then is a copy and ROM, then print and ROM. If the needs to change the execution, then having the copies is fine. Map2 will be implemented in this manner. However, if the run does not change the structure, then you could put a single copy in ROM and headband will be in RAM, but the linked list will be in the ROM. Okay. It is possible to create linked dynamic and grocery as okay. However, in or go simple. Okay, we will refrain doing dynamic allocation, which would require management of a heap. Most of the time, do not allow the heap to be accessed by the application because this. Okay. Linked list is a data type that consists of a pointer to its own data type, which will be the next node, and also a data. What ways is it better than array? It can be how to say it? You can add another node inside of the linked list, and then you can also easily search into the linked list compared to the array. Yep. Yeah, it can grow a string, you can add and you can sort out dynamically. Next. Oh, that's fast. Oke guys, sepertinya kayak udah cukup malam. kita istirahat dulu. Saya mau makan, mau telepon dengan seseorang. Kita cukupkan dulu hari ini streamingnya. Terima kasih buat Akmal hari ini, terima kasih buat yang nonton walaupun gak ada yang nonton.